Assalamu alaikum and good morning. Today we're going to continue with topic 18, carboxylic acid and esters. So previously we've looked at the general properties of carboxylic acid, the physical properties of carboxylic acid, the production of carboxylic acids. So now we're going to look at the reactions of carboxylic acids. The learning objective that we are going to cover is the redox reaction with reactive metals to produce salt and hydrogen, the neutralization reaction of acid with alkalis to produce salt and water, the acid-base reaction with carbonates to produce a salt and water and carbon dioxide. So in the last lesson, we've talked about how carboxylic acids behave as an acid, where it dissociates to release a hydrogen ion. So this is similar to how normal acids, like inorganic acids, for example, your hydrochloric acid, nitric acid, sulfuric acid, would react with alkali or metals or carbonates. The only difference is in the salt that is produced. Okay, so just to recall back that when carboxylic acid dissociate in aqueous solution, it releases the hydrogen ions from the hydroxy group of the COOH, and the anion, which is the rest of the molecule, the rest of the carboxylic acid, and this anion is called the carboxylate ion. So it doesn't matter how many carbon atoms are attached to this carboxylic acid, the dissociation is occurring at the OH bond. Okay, so just keep this in mind, the carboxylate ion, because the salt that is being produced in the reactions that we're about to see after this will involve the formation of carboxylate ion with a countercat ion that usually comes from the alkali. Okay, just like how normal acid-base reaction would happen. Okay, so moving back to this part. Okay, so we're going to look at the first reaction of acids with an alkali to form a salt and water. So if this was a normal acid like HCl reacting with an alkali that is sodium hydroxide, we would form the salt. Okay, so we would form water. So I'll just write it as H2O. And the salt would be from sodium and from the Cl from HCl. Okay, so our salt is NaCl. Okay, whereas if we're looking at organic acid, which is a carboxylic acid, I am going to use ethanoic acid as an example, CH3C. So I'm just going to focus on the COOH part of the carboxylic acid, because that's the functional group and that's where the reaction is happening. Okay, whereas the rest of the molecule, the hydrocarbon tails, will stay unchanged. Okay, plus, so an alkali here, the easiest one I would use is sodium hydroxide to form the general equation would give a carboxylate salt. So I'll leave the carboxylate salt for later. And I would just write down the other product first, which is H2O. I'm using green, but you know that the water is coming from the hydroxide ion of your alkali and the hydrogen ion from the acid. So when it combines H plus and OH minus, they form H2O water. Okay, so now I want to talk about the salt. Okay, so imagine during the acid-base reaction, the OH bond is broken. So I'm left with this carboxylate salt that comprised of the CH3COO minus species, okay? And this is called the ethanoate ion, okay? Ethanoate because there are 2 carbon and it is a member of a carboxylate species, okay? So my anion would be CH3COO minus, okay? And the counter ion would be a cation, and the cation would come from the alkali, and that happens to be the sodium ion. So I now have that, okay? So when this negative ion and positive ion combine, they become a neutral species. So you can do it with or without the charge, okay? In this case, it doesn't confuse you because it's just they are only they're both +1 and -1, so they cancel out nicely. If you don't want to draw it without the charges, you can of course remove it, and they're still the same species, they're still the same salt, and we call this sodium ethanoate, and the eth comes from the 2 carbon here, okay? And this originates from ethanoic acid and sodium hydroxide. Okay, so everything else, just make sure that everything is balanced. Well, in this case, they're all balanced again because it's the charges cancel out nicely. Okay, next reaction we're going to look at is the reaction of carboxylic acid with metal. Just like a normal acid metal reaction, you would form a salt and a hydrogen gas. Okay, this time the salt will be of carboxylate salt. I'm going to use a different acid just so you can see that it works with any acid. Propanoic acid, CH3, CH2, COOH. Okay, so I'm only drawing out the functional group plus magnesium metal, which is a solid, to form, okay, the easier product would be hydrogen gas, okay, and the salt, right? So you imagine you are, because it is behaving like an acid, so you are breaking the OH bond, you are releasing the H plus ion from the propanoic acid, and you're left with carboxylate ion, which is called the propanoate ion, okay? And it also has a charge of -1. So you can imagine if if hydrogen ion is +1, the carboxylate ion, the propanoate ion would be would have a charge of -1. Okay, so then my product is CH3, CH2, COO minus. Okay, so that's your propanoate ion. And the counter ion, which is the cation, would be of magnesium. Now remember, magnesium is 2+. Notice that there is a mismatch in charge. Okay, so what do you have to do? Remember this rule where you bring down the charge across for an ionic compound, okay, when the charges don't match or don't cancel out. So what happens is that if I were to draw this using a gray, okay, so you bring down the 2 and you bring down the 1 across. So that means CH3, CH2, C double bond O is now 2 lots, and my Mg is now 1. Okay, so that means you have 2 units of the propanoate ion. Since it has a charge of -1, you need 2 of them to cancel out the charge 2 plus from magnesium. Okay, so once you have done this, you don't need to write down the charges anymore. Okay, so that means to balance out the charges of 1 magnesium, you need 2 units or 2 lots of propanoate ion. Okay, so the name of this is magnesium propanoate salt. Okay, and this originates from propanoic acid. So just be careful when the charge is not 1-to-1. Okay, so they don't cancel out. When I said 1-to-1 means they are not the same charge. Like if it's +2 and -2, then you don't have to worry about it because they cancel out nicely. Okay, so the formula of magnesium propanoate is, well, some of you may ask, is it a problem if we write it like this? Mg CH3 CH2 CO2 2. Of course, there's no problem. Whether you put the magnesium at the front or you put the magnesium at the back, it does not matter. I like to put them next to each other so you can see the charges clearly. Okay, so these 2 notations are correct. Okay, and the most important thing is you need 2 units of the propanoate ion to cancel out the charge of 2 plus of magnesium. Okay, now if this was a group 1 metal, sodium, of course, no problem because the propanoate ion is -1, sodium is +1, so they cancel out nicely, and you don't have to worry about bringing the charge down and across. Okay, next example is reaction of carboxylic acid with carbonate. Okay, so you already know that it will form salt, carbon dioxide, and water. So I'm going to use another example of acid, butanoic acid, 1, 2, 3, and 4. So that's a butanoic acid. Oh, before I forget, to balance my equation. Sorry, I need to balance the equation. So I need 2 molecules of propanoic acid because I also form 2 units of the propanoate ion. Okay, and then everything else should be balanced nicely. Okay, next is butanoic acid plus sodium carbonate to form carbon dioxide and water. Okay, those 2 are pretty standard. The ion, the salt that you would produce would be butanoate ion, CH3, CH2, CH2, COO minus, and then the counter ion, which is the cation, will be Na plus. Okay, so, and that cancels out nicely, so you can just write it as like that. It's the same. Okay, and we call this sodium butanoate. The but, of course, comes from the number of carbon atoms, including the one that is on the COO minus part of the molecule. Okay, this carbon. Okay, so this works with any carboxylic acid, any alkali, any metals, and any carbonates. Okay, usually what I mean by any, of course, they usually come from the group 1, group 2 metals. Okay, because the rest of the group, they behave differently. So usually we deal with group 1 and group 2 metals only. Next is reaction with lithium aluminium hydride to form a primary alcohol. So basically this is just the reverse of the oxidation of primary alcohol. Okay, so carboxylic acids can be reduced to their corresponding alcohol. Now in questions, you have to specify the type of alcohol. Okay, you don't just answer alcohol. You need to say if it's primary, secondary, or tertiary. And as a matter of fact, carboxylic acid can only be reduced to primary alcohol. Okay. The reagent is lithium aluminium hydride, or the full name lithium tetrahydridoaluminate. You just have to memorize the formula LiAlH4, and remember that it has to be in dry ether. Dry ether is the solvent. We don't use aqueous lithium aluminium hydride because they will react explosively. Okay, so water will react with lithium aluminium hydride and it wouldn't be acting as a reducing agent. So in equation, reducing agent is written as square bracket H. It follows the concept of reduction, which is gaining in hydrogen. Okay, and the other product would be water. Don't forget to balance your equation. Next is just showing you the equation. Okay, so I will just draw out and displayed formula. Okay, so if you started with an ethanoic acid, you would expect to end up with a primary alcohol, the corresponding alcohol, which is ethanol. You must not add or lose any carbon atoms. Okay, so then you add 4 hydrogens to give you. Okay, so I'm just going to draw what's already on the molecule. Sorry. Since it becomes an alcohol, you will be adding. Okay, but actually the mechanism is much more complicated than that, but so you don't have to worry. So you're adding 2 hydrogens onto the alcohol, and the other 2 hydrogens are for the formation of water. And again, you don't have to worry about how that works. Okay. Okay, so just make sure that you always balance any reduction equation or oxidation. Well, any equation, really. Okay. Next is reaction of carboxylic acids with alcohol. So this, you know that this is already an esterification reaction. You usually use concentrated sulfuric acid as catalyst, and so this actually covers 2 learning objectives, 18.1.2 and 18.2.1, which is under esters. Okay, right, so this is under the formation of esters. Carboxylic acids react with alcohols in the presence of a strong acid catalyst to form esters and water. So don't forget that you form water as a side product, and this means that esterification is a condensation reaction. Okay, you have 2 reactants to combine into one which is your ester, and in the process you form water. So that's condensation reaction. Condensation reaction for carboxylic acids and alcohols are often reversible. Reversible means they can go forward, ester formation, or they can go backwards, which is ester hydrolysis. Remember your ester hydrolysis, the breakdown of ester in the presence of water. So forward can happen, reverse also is happening, and that's not good. If you are aiming for the production of ester, you do not want the ester to be broken down. So this reaction is actually it has low yield. Okay, yield means the product, the amount of product that you get, right? So the reaction is quite slow and needs heating under reflux, and you also get low yields, 50%, right? Here is an example of an esterification reaction. Now, I don't really like how the diagram is drawn, because the way I would draw it is usually I put the functional groups next to each other. So I noticed when you did the question, one of the questions where it requires you to draw the ester products, and a lot of you actually got confused on how to draw the ester. So my advice is to always place your carboxylic acid next to your alcohol in such a way that you flip this diagram. Okay, you flip it horizontally so that your OH is now next to COOH. Okay. So what happens during esterification process is that we lose the OH of the carboxylic acid, and we lose the hydrogen of the hydroxy group from alcohol. Okay, together they form H2O, and then we form the ester bond COOC. Okay, more specifically, the ester bond that is being formed is this C single bond O. Why is it important to highlight that C single bond O? Is because that is the same bond that is being broken during hydrolysis. Okay, so new bond formed is also the bond broken during hydrolysis. Hydrolysis is the reverse. Okay, and then we think about the naming of the ester. Okay, so I usually extend the functional group of ester from C double bond O all the way to that carbon directly attached to the oxygen. Okay, so one common mistake for students to do is, just because that the alcohol is drawn like this with the carboxylic acid, you automatically think, yes, this hydrogen will combine with the hydroxy group on the carboxylic acid to form water, and that's where my ester is forming. This hydrogen is attached to carbon, so it will not get involved in the reaction. It has to be the hydrogen that is directly attached to oxygen. Okay, and remember, carboxylic acid only reacts with alcohol. Carboxylic acid will not react with another carboxylic acid. Alcohol will not react with another alcohol. Okay, when it comes to naming, we always name the alcohol part first. Now, how do you know who is the alcohol part? The alcohol part is usually the one with the single bond O, like here. That's the part that came from the alcohol. Okay, anything that is directly attached to the C double bond O comes from the carboxylic acid. Okay, so I will just label the blue one as being ester bond. So if we name ester, we usually start with the alcohol bit. Okay, we count the number of carbon atoms only, excluding the oxygen. So that's 1, 2. So that's ethyl. Okay, And then the carboxylic acid part, 1, 2, including the carbon on the C double bond O. Yes. So that is called the ethanoate. So it's ethyl ethanoate. Okay. I think in the next slide, it will show you again the naming. All right. So the naming of esters, the bit ending in YL comes from the alcohol. So that means this part is alcohol. Okay. And the other part, the other side of the part is the carboxylic acid. Okay, so let me just go through this quickly. The alcohol part only has one carbon, so that is a methyl. Okay, the carboxylic acid, 1, 2, 3. There's 3 carbons, so that's a prop. So it's called the methyl propanoate. Okay, another thing that you have to be careful is with the structural formula. Okay, let's see. I think I'll do it here. Okay, so you notice that it's CH3COO, CH2, CH3. So that means we start with CH3 over here, CO, and then single oxygen. So you can combine them, CH2, CH3. Okay, now what if it's drawn with the alcohol parts first? So now maybe I'll use a new page so you can copy this down. Okay, what if the structure is now drawn like this? CH2. Okay, so I suggest you to copy this down, what's wrong and what's right. Okay, so if I were to write down the structural formula, this time I've got the alcohol group on the left and then the carboxylic acid group on the right. Okay, whereas in this example, you've got the carboxylic acid group on the left and then the alcohol on the right. Okay, so when you write this down, I will start with CH3. Okay, and then some students, because they see that the oxygen and the C double bond O is next to each other, they think that they can write CH3COO. Okay, because it's, you know, CO and then oxygen. Now the problem with this is, if I just continue writing down, okay, now the problem with this is that CO represents this CO and the single O represents the alcohol oxygen. Okay, so you can see that in terms of my arrow, it's already overlapping. So this is not the correct way of writing down your structural formula. Okay. Okay, I'll draw the actual molecule of that later on. Now, how do you write this formula correctly? CH3O for the oxygen on alcohol, CO followed by CH2, CH3. Now that is correct. Okay. What is CH3, COO, CH2, CH3? What does this formula represent? It would represent this molecule, which is different. COO these two are not the same. Okay, maybe I should change the color, otherwise you would think maybe red. Okay, now the diagram in red is an ethanoate. And the structural formula is CH3COO, CH2, CH3. Okay, whereas the one in blue here is a methyl propanoate. Okay, so be careful there. So you can copy this down in your notes just to remind you on how to write down the structural formula. Okay, so if the alcohol part comes first, you must write down the O, single O, and then followed by the CO. So you will write it as OCO. Do not combine it as COO. Okay, because that will give you a different structure, which is this one. All right, so that is all for this topic. Okay, don't forget, as usual, fill in the post-test questions on forms, and the link to forms can be found in the description box of this video. Okay, Assalamu alaikum and thank you.